The inverse of a matrix formula. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we spent some time exploring how to calculate the determinant of a matrix and understanding the concept of the adjoint. Today, we are going to bring those two pieces of the puzzle together to achieve something much more powerful: finding the inverse of a matrix. Now, if the term inverse sounds a bit abstract, let's look back at something you've known since primary school: basic arithmetic. You remember that the multiplicative inverse of a number, let's call it a, is 1 over a, also written as a to the power of -1. The whole point of this inverse is that when you multiply the original number by its inverse, the result is simply 1. In the world of matrix algebra, we apply that exact same logic. If we have a square matrix, which we will call A, its inverse is another square matrix, which we denote as A inverse. The defining characteristic here is that when you multiply matrix A by its inverse, the result is the identity matrix, which we represent with the letter I. To put this into a formal mathematical statement, if it was a square matrix of order n, then A inverse is officially considered the inverse of A if A multiplied by A inverse, which is equal to A inverse multiplied by A, results in the identity matrix I. The formula for the inverse. For any square matrix A, the inverse can be found using this specific formula. A inverse equals 1 over the determinant of A, multiplied by the adjoint of A. To make sure we are all on the same page, let's break down what those two components are. First, the vertical bars around A represent the determinant of matrix A, which we discussed in our previous lesson. Second, A refers to the adjoint of matrix A, which is a matrix we've also recently explored. However, before you jump into these calculations, there is one crucial condition you must always check. The inverse, A inverse, exists if and only if the matrix A is what we call non-singular. In practical terms, this simply means that the determinant of A must not be equal to 0. Why is this so important? Well, if the determinant of A is exactly 0, we call that a singular matrix. In this case, the inverse simply does not exist. If you look back at our formula, a 0 determinant would force us to divide by 0, and as you know from basic arithmetic, division by 0 is undefined. So, always check your determinant first to see if the journey is even possible. Now that we understand the concept of what an inverse matrix actually represents, let's look at the actual formula you'll use to calculate it. Step-by-step process to find a -$1. Now that we understand the definition of an inverse matrix and the formula itself, let's break down the actual procedure. Finding an inverse might look intimidating at first, but if you follow these 4 manageable steps, you'll find it's quite systematic. Step 1, your very first task is to calculate the determinant. You need to find the value of the determinant of matrix A. This is a crucial checkpoint. As we mentioned in the previous slide, if the determinant equals 0, you must stop right there. The matrix is what we call singular, meaning it simply has no inverse. There is no point in proceeding further if the determinant is 0. Step 2, once you've confirmed the inverse exists, you need to find the matrix of cofactors. This involves calculating a specific cofactor for every single element within your matrix. To do this, you'll need to recall the formula for a cofactor, which is -1 raised to the power of I plus j multiplied by the minor of the element. Essentially, you are applying a specific sign pattern to the minors we've studied previously. Step 3, next, we need to determine the adjoint of matrix A. To get this, you take the cofactor matrix you just created and find its transpose. Remember, the adjoint is not just the cofactor matrix itself, it is the transpose of that cofactor matrix. This means you'll be switching your rows and columns. Finally, step 4. It's time to apply the actual inverse formula that we introduced at the start of this lesson. You will take your adjoint matrix and multiply it by the scalar 1 over the determinant of A. In practical terms, this just means you take every individual element inside your adjoint matrix and divide it by the determinant value you found in step 1. If you follow these steps carefully, as we will demonstrate in the detailed example coming up next, you'll arrive at the correct inverse every time. Real-world application, cryptography. Now that we understand the mathematical formula and the step-by-step process for finding an inverse, you might be wondering, when would I ever actually use this in real life? Well, let's look at a fascinating application in the world of digital security and cryptography. In the realm of digital security, matrices are actually used as powerful tools to encrypt messages so they can be sent safely across the internet. Imagine you have a secret message. We can convert that message into a matrix, which we'll call matrix M to hide the content. We multiply this message matrix by what we call an encoding matrix. Let's call it matrix A. The result of this multiplication is a new matrix, which we call matrix C, representing the ciphertext. This is the scrambled, unreadable version of your message. Mathematically, we express this as matrix A multiplied by matrix M equals matrix C. But here is where the concept we just learned becomes essential. For the receiver to read the original message, they need to unscramble that ciphertext. To do this, they must multiply the ciphertext matrix by the inverse of the encoding matrix, which is matrix A inverse, multiplied by matrix C. This process recovers our original message matrix, M. As you can see, the entire security of this system relies on the existence of that inverse. Without the inverse matrix, the message remains encrypted and unreadable. This perfectly demonstrates why the condition of a non-zero determinant is so critical. If we couldn't find the inverse, we could never decrypt the message. Now, let's move on to a concrete numerical example to see this formula in action. Detailed example. Our problem today is to find the inverse of matrix A, where the first row contains the elements 2 and 1, and the second row contains 3 and 4. Let's begin with step 1, calculating the determinant of A, denoted as the vertical bars surrounding A. To find this, we multiply the elements of the main diagonal, which is 2 times 4, and then subtract the product of the off-diagonal elements, which is 1 times 3. This gives us 8 minus 3, resulting in a determinant of 5. Now, referring back to our rule about non-singular matrices, since our determinant is 5, which is not equal to 0, we can confirm that the inverse definitely exists. Moving on to step 2, we need to find the cofactors. For a 2-by-event matrix, this involves finding the value for each position. The cofactor for the first row, first column is 4. For the first row, second column, it is -3. For the second row, first column, it is -1. And for the second row, second column, it is 2. Next, step 3. Finding the adjoint of A. First, we arrange those cofactors into a cofactor matrix, which looks like 4, -3 in the top row and -1, 2 in the bottom row. To get the adjoint, we take the transpose of this matrix, which means we switch the rows and columns. So, our adjoint of A becomes 4, -1 in the top row and -3, 2 in the bottom row. As a quick tip for your exams, for a 2-by-2 matrix, you can achieve this same result simply by swapping the elements on the main diagonal and changing the signs of the other 2 elements. Finally, step 4, we apply our master formula. We take 1 divided by the determinant, which is 1/5, and multiply it by our adjoint matrix. When we distribute that 1/5 to every element inside the matrix, we get our final answer. The first element is 4/5, the second is -1/5, the third is -3/5, and the fourth is 2/5. Now that we have walked through the theory and the step-by-step process, let's put everything we've learned into practice with a detailed example. As we move to the next slide, I want you to pay close attention because I'll be highlighting some common pitfalls where students often lose marks during this exact process. Common mistakes to avoid. First, please do not ignore the determinant check. I have seen many students jump straight into the heavy calculations of the adjoint without first checking if the determinant of A equals 0. Always calculate the determinant first. If the determinant is 0, you can stop immediately because the inverse simply does not exist. Second, watch out for forgetting the transpose. This is a very frequent mistake. Many students calculate the matrix of cofactors and stop there, but remember, the adjoint of A is the transpose of the cofactor matrix. You must flip the rows and columns to get the correct adjoint. Third, be extremely careful with sign errors in your cofactors. Remember that the cofactor formula involves the term -1 raised to the power of I plus j for larger matrices, like a 3×3. This creates a checkerboard pattern of plus and minus signs. If you miss even one sign change, your entire final matrix will be incorrect. Finally, pay close attention during the scalar multiplication step. When you multiply the adjoint matrix by 1 divided by the determinant of A, you must ensure that this fraction is multiplied by every single element inside the adjoint matrix, not just the first one. Now that we have walked through the step-by-step process and seen a practical example, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that lead to the wrong answer. If you can avoid these 4 mistakes, you will be well on your way to mastering matrix inversion. Let's wrap up with a quick summary of what we have learned today. Key takeaways. First, remember that the inverse of a matrix A is denoted as a inverse, and its defining property is that when you multiply matrix A by its inverse, the result is the identity matrix, which we call I. Second, keep the core formula at the front of your mind. A inverse equals 1 over the determinant of A, multiplied by the adjoint of A. This formula is the heart of everything we've practiced today. Third, and this is a vital point to remember for your exams, a matrix is only invertible if it is non-singular. In practical terms, this means you must check that the determinant of A is not equal to 0. If the determinant is 0, the formula fails because, as we discussed, division by 0 is undefined. Finally, if you ever feel overwhelmed by the calculation, just remember the logical flow of the process. Start with the determinant, move to finding the cofactors, then determine the adjoint, and finally, apply the formula to reach the inverse. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear in your mind. If you can master this sequence, you can solve any inverse matrix problem. Great job today.